Hi guys, I am Venkat Sai from IRA College. This is my contributor presentation on applied physics subject. I have elected this topic as my concept presentation. First, we go through the topic. Our topic is thermal radiation. Thermal radiation. Thermal satellite sensors. Landsat thematic mapper. Landsat for inwards. Advanced multispectral scanning with improvements over MSS. Higher spatial and radiometric resolution. Fine spectral bands. 7 versus 4 spectral bands occur simultaneously. Band 6 senses thermal and infrared radiation. Landsat can only acquire night signs in band 6. Here you have channel wavelength range and resolution. Okay, here how is EMF generated? Video generated by periodic currents of electric charges in voice. Microwave generated by electron tubes that use the motion of high-speed electrons in specially designed structure to generate EV fields. Visible. High frequency wave in the infrared and visible when generated by molecular excitation. Vibrational or invert orbital followed by decay. The emitted frequency is exactly related to the energy difference between the two energy level of the molecules. Heat kinetic energy of the random motion of particles of the matter. The random motion results in excitation, electronic vibrational, electronic vibrational rotation due to collisions followed by random emission of EM wave during the decay. Because of its random nature, this type of energy transmission leads to emission over a wide spectral band. Here is the electromagnetic spectrum frequencies and rays types. First we have gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio, TV, long rays. Okay, thermal radiation. Thermal radiation is emitted by all objects at absolute zero, minus 2.2, minus 273.15 centigrade. Spectrum of this radiation, that is intensity versus wavelength, usually follows the idealized black body radiation curve. Stephen Boltzmann law. Total energy emitted over time by a black body is proportional to T4. Phase displacement law. The wavelength of the spectral peak is proportional to T. Here is some Kelvin temperatures according to the thermal radiation. For 79 K liquid air, 195 K dry ice, 1300 K earth, 1800 K red hot object, 3000 Kelvin tungsten filament, 6000 Kelvin sun. Okay, what is a black body? The black body emits a temperature dependent spectrum of light. Thermal radiation from a black body is termed black body radiation at room temperature. PBS emit mostly infrared light, but as the temperature increases past a few hundred degrees centigrade, BV starts to emit visible wavelengths shorter and shorter. Red, E, orange, yellow, white, B, blue. Beyond this, the emission includes increasing amounts of warming. Here is the wavelength color of BB radiation depends on the temperature of BB. The temperature also varies from the black body. Okay, next one. The black body is an idealized object that absorbs all EMR that falls on it. No EMR passes through it and none is reflected. Perfect emitter and a perfect absorber. All incident radiation is absorbed. Black body emits all possible radiations. Because no light visible EMR is reflected or transmitted, the object appears black when it is cold. We can see through this object, this picture. Okay. Black body lab experiment. An object of controlled temperature. Here is object means this picture we can observe that what will be the object will be. An object of controlled temperature T contains a cavity joined up to the outside by a small hole. If the hole is small, the radiation in the cavity comes to equilibrium with the walls. The hole always is small fraction of the radiation to pass to a spectrometer. The radiation coming out has the small spectrum as what is inside. Here is a graph also represented. The graph also represents the black body lab experiment. Okay. Next, we go to the next slide. Plot of Planck's radiation of for two temperatures. Note that the peak of the curve moves to the left as the temperature increases. Hotter objects output a larger fraction of their EMF at shorter wavelength. Note also strong dependence on temperature of the total emission. The radiancy is the power emitted per unit area per increment of wavelength and so has units of Weber meter per minus. Describing angular distributions of radiation. Consider a plane surface illuminated by EMR from a variety of directions. Two angles are needed to specify a particular direction of incident radiation. Theta, angle between incident and normal to the surface. Psi, azimuthal angle measured around normal in place of the surface. Consider element dA of the surface and radiation incident over range of angles theta to theta plus d theta and psi to psi d theta. Solid angle d omega equals to sin theta d theta d psi. Power incident of the element dA from this range of directions is proportional to dA and d omega, and a term L which gives the strength of the radiation. dP equal to L cos theta dA dL is radius. SI units is Weber meter square meter per power minus s units. Spectral radiance. Spectral radiance L lambda is defined as the radiance delta L contained in a small range of wavelengths delta lambda and given by delta L equals to L lambda delta lambda. L lambda is the differential of the L written x written lambda. L lambda equals to L by Z. Okay, spectral radiance SI units is Weber meter universal SR universal. Okay. Radiance. Spectral distance L lambda is the radiant flux per unit solid angle leaving an extended source in a given direction for unit projected source area in the direction. Radiant flux in certain wavelengths leaving the projected source area within a certain direction and solid angle L lambda equals to delta by Z by A cos theta. Stephen-Boltzmann law. The total emitted radiation from a black body is proportional to the fourth power of its absolute temperature. M lambda is equal to omega t power 4, where lambda is Stephen-Boltzmann constant 5.6697 into 10 to the power of minus 10 omega Weber meters minus 2 Kelvin per power minus 2. U is the amount of energy emitted by objects such as the sun or three. The earth is a function of its temperature. This is can be derived by integrating the spectral radiance over the entire spectrum. L equals to 0 to infinity, integral of 0 to infinity L lambda d lambda equals to 2 pi power 4 k power 4 by 15 c square h cube t power 4 or m equals to t t L equals to psi t power 4. Okay. Why is displacement draw? In addition to computing the total amount of energy exciting a theoretical black body such as the sun, we can determine its dominant wavelength based on Wien's displacement law. Lambda max equals to k by t, where k is the wave displacement constant, equals to 2.898 into 10 to the power of minus 3 km, and T is the absolute temperature in K. That is, there is an inverse relationship between the wavelength of the peak of the emission of a black body and its temperature. Therefore, as the sun approximates a 6000 Kelvin black body, its nominal wavelength lambda max is 0.48 millimeter. Real genes approximation. Convenient and accurate description for spectral radiance for wavelengths much greater than the wavelength of the peak in the black body radiation formula. That is lambda greater than lambda max, lambda equal to 2 kt by lambda power 4, or LV equals to 2 kt v square by c square. Approximation better than 1% when c by lambda kt less than 1, or lambda t greater than 0.77 m Kelvin. For example, for a body at 300 Kelvin, the approximation is valid when lambda greater than 2.57. In other words, this approximation is good when viewing thermal emissions from the Earth over the microgram band. Okay. Black body radiation curves. Black body radiation curves for several objects, including Sun and Earth, approximate 6000 Kelvin and 300 K black bodies. As the temperature increases, dominant wavelength lambda max shifts towards shorter wavelengths. Area under each curve may be summed to compute the total radiant energy exciting each object. Okay. Real materials. Real materials are not black bodies, so we introduce a property emissivity F's law. Describe the actual absorption and emission properties of real objects like gray bodies is wavelength dependent. The law of lambda. is the ratio of the energy radiated by the material to the energy radiated by a black body at the same temperature is a measure of a material's ability to absorb and radiate energy has a value from 0 to 1 n lambda equals to epsilon of lambda n lambda p. Black body radiance, gray body, a body that reflects a fraction of the incident radiation reflexivity is 1 minus epsilon lambda. Temperature of lava flow. The temperature of a Fahrenheit lava flow can be estimated just by observing its color. The result agrees well with the measured temperature of lava flow at about 1000 to 200 centigrade. The thermal radiation. Thermal cameras and imaging systems respond to infrared radiation and suitably calibrated for emissivity can produce images of their surface temperatures. This picture shows a false color is between the display. Thermal remote sensing strengths, good resolution accuracy, long heritage 20 years brightness, obscured by clouds, atmospheric corrections required, sea surface temperature, thermal radiation from emitted thermal radiation from both the atmosphere and land surfaces with color resemblance of red, yellow to warm and green blue out to color. Fire monitoring. Images of 1988 Yellowstone fires visible image is what would you see flying over a forest fire smoke. Bright image combines several infrared bands reflecting thermal infrared to cut through the smoke. Bright yellow areas are actively burning fire lines. Visible channels and thermal channels. That's all about the picture.